All right. So we had just finished talking about unit vectors in the last video. The last thing that remains for us to talk about is the dot product and one application of it, which is finding angles between vectors. So I'm going to start with just the definition of what a dot product is. Now notice we've defined one type of multiplication with vectors. We've called it scalar multiplication, and it's what you do when you multiply a real number to a vector. Notice it's not multiplying two vectors together. It's multiplying a scalar, which is just a number, a real number, to a vector, which is a different type of thing. The dot product is a type of product that multiplies two vectors together. So it's very different from what scalar multiplication is. Now there are a couple of different types of products that we can take with vectors. You may have heard of something called a cross product. It's impossible to take cross products with the types of vectors we're dealing with here. You can only take cross products of vectors in three-dimensional space. They require three components for that definition to work. We don't cover cross products in this class. That's going to be covered in Calculus 3, or you may see it in a different class, physics or something like that. Our focus here is the dot product. Now here's the interesting thing about the dot product. The dot product multiplies, in a sense, two vectors, but the result of that product is not a vector. The result is a scalar, just a number. Okay, so I'm going to give you the definition. We'll do an example, and then it's not going to seem all that useful of a definition because it's not immediately obvious what this could possibly be useful for, but we'll talk about one application of it down here. It's actually extraordinarily useful in a number of different ways. So the way you perform a dot product, if you have these two vectors in component form, is we multiply their corresponding components together. Here I'm multiplying A1 with A2, the horizontal components, and then I multiply B1 with B2, the vertical components. Once I've multiplied those, I sum the results. So here's an example. I want to evaluate the dot product of -1, 4 with 3, 9. Very easy. I just multiply the horizontal components and add that to the product of the vertical components, 4 and 9. This would be -3 plus 36, which is 33. Notice I got a scalar. I did not get a vector. That's what dot products do, is they produce these scalars. They can be positive, negative, 0. In fact, when there's 0, that represents something very specific, which we'll mention here in a moment. But what is one way of using this idea of the dot product? Well, if you have two vectors, u and v, and we give them the same initial point. So let's say this is u, this is v. And if I want to know what the angle between those two vectors is, which is actually a really useful thing to know in a lot of applications, I have a formula that can give me that angle, and that formula involves the dot product. It shows up right here. So the cosine of that angle right there is going to equal the dot product of these two vectors divided by the product of their magnitudes. That way, if I want theta, the angle between them, I can just evaluate this and then take the inverse cosine of it. I want to show you where this comes from. And then once we've done that, I'm going to do a couple of examples using this idea. All right, so again, let's suppose that we have these two vectors here. U and V. And I'm going to, let's say that U equals A1, B1, V equals A2, B2. Okay? One thing I want to point out, I find that I keep doing that, I'm not paying attention to where the page is. One thing I want to point out is that if we take the dot product of a vector with itself, for example, u dot u, that would be a1 times a1, or a1 squared, plus b1 times b1, or b1 squared. That's the same thing as the magnitude of u squared. Did you notice that? If I take a square root of this, square root of a1 squared plus b1 squared, that's how we define the magnitude. So the dot product has a direct relationship with the magnitude of a vector. When you dot a vector with itself, it's the same as squaring the magnitude of that vector. Now, this is the angle theta that we've been talking about. And this, if you remember, would be the vector u minus v. Okay? Now, if I've connected these terminal points together with the vector u minus v, which means I've created a triangle. And if I know the lengths of these sides here, which the lengths of these sides would just be the magnitudes of these vectors, then I can use something like the law of cosines to find a relationship with this angle. So again, let's use the law of cosines here. I know from my law of cosines that this opposite side here, if I know its magnitude, the magnitude of u minus v squared will be equal to the magnitude of u squared plus the magnitude of v squared minus 2 times the magnitude of u times the magnitude of v times the cosine of that angle theta. Okay? Let's look for a second at this guy right here. So I'm going to do a little work on that. Based on what we talked about up here, the magnitude of a vector squared is the same as taking the dot product of a vector with itself. So that this is equal to the vector u minus v dotted with the vector u minus v. Like that. Okay? But u minus v, remember I put that in component form up there, u minus v has, if I subtract these components, its x component would be a1 minus a2. And so this is going to be a1 minus a2 times a1 minus a2, or a1 minus a2 squared. Similarly, I have b1 minus b2 squared. Expanding this out, I'm going to get a1 squared minus 2a1a2 plus a2 squared. That's expanding this, plus b1 squared minus 2b1 b2 plus b2 squared. Okay, now I'm going to do a little regrouping. Group the a1 squared plus the a2 squared plus group the b1 squared plus b2 squared, and then group up the terms with negative 2's and factor the negative 2 out. Negative 2 times a1 a2 plus b1 b2. Okay? Notice this thing right here is this. It's the square of the magnitude of u. So this could be written as the magnitude of u squared. Similarly, that's the magnitude of v squared. This guy right here is, by definition, the dot product of u with v. Notice that would be a1 times a2 plus b1 times b2. That's what gives me the thing in the parentheses. So this is minus 2 times u dot v. All of that is equal to the left-hand side of this equation. So I get magnitude of u squared plus magnitude of v squared minus 2 times the dot product of u with v. And that's equal to the magnitude of u squared plus the magnitude of v squared minus 2 times the magnitude of u with v times the cosine of theta. Okay, tons of things cancel. Magnitude of u squared, I can subtract that from both sides. Magnitude of v squared, I can cancel that from both sides. Now I have a single term on both sides, each of which is being multiplied by negative 2. Divide the negative 2's. That gives me the dot product of u with v equals the magnitude of u times the magnitude of v times the cosine of theta. If I divide both sides by this product of magnitudes, I get cosine of theta equals the dot product of u with v over the magnitude of u times the magnitude of v. That's that formula that we just mentioned on that previous page. Okay? So really it all boils down to the law of cosines here. All right. So that's a proof of that. Let's do an example where we want to find the angle between two vectors. Okay, so our goal here is to find the angle between the vectors 2, 5, and 1, -1. I could graph these vectors as position vectors and then sort of represent the angle between them just to get a sense of what this looks like, but I'll let you do that if you want to see it that way. In order to do this, I'm going to use that formula which says I needed the dot product of these two things divided by the product of their magnitudes. So let's start by finding their dot product. 2, 5 dotted with 1, -1. That would equal 2 times 1 plus 5 times -1, which is -3. Now we need the magnitudes of each one of these. Magnitude of 2, 5. That's equal to the square root of 2 squared plus 5 squared, which is root 29. I need the magnitude of the other vector. 1, -1. Square root of 1 squared plus -1 squared, which is root 2. Okay? According to our formula then, the cosine of theta, the angle between the two vectors, is equal to the dot product, which we found to be -3, over the product of these magnitudes, root 29 times root 2. So, theta then would be the inverse cosine of that, -3 over. Now, if I wanted to, I could leave this as is, or it's a square root times a square root. We have a property that says we can multiply what's under those square roots, so that would be the square root of 58. If I want this in degrees, I would plug it into a calculator and I get something that's approximately 113.2 degrees. Okay? Cool. Last thing, same concept. We're looking at angle between vectors, but I'm going to use an application. This is an application that comes straight out of your book. It's the last example in section 10.8, and I just want to walk through it because I like this example. Expect to see something like this on the test. So we have an airplane that's flying at an airspeed of 200 miles per hour on a southeast bearing of 140 degrees. It says a north wind is blowing at 16.2 miles per hour, and what we want are the ground speed and actual bearing of the plane. So first of all, vectors, we said, can represent forces. They can also represent velocities. They're very commonly used for that as well. A velocity is the speed of something with direction. So if an airplane is flying at a 200 mile per hour or 200 mile per hour airspeed with a southeast bearing of 140 degrees. First of all, when we talk about bearing, bearing is an angle measured from north. Okay, so if this is north, then the plane is traveling at an angle that's measured clockwise. Bearing is actually measured clockwise, 140 degrees from north. Okay, the length of this vector would be 200 because it represents the speed, 200 miles per hour. And it says a north wind is blowing at 16.2 miles per hour. This terminology confuses a lot of people. The north wind is actually blowing south. By saying north wind, what we mean is it's blowing from the north, not toward the north. So the north wind is blowing at a speed or a velocity of 16.2 miles per hour. And again, the direction will actually be south. So the way we want to think of this is that there are two forces acting on this airplane. There's the force of its own jets, which is giving it direction and speed, which we've indicated by this arrow. But then there's a secondary force, a secondary velocity acting on that plane, and that's going to be represented by the wind. So the true speed and bearing of the plane are going to be given as the sum of those forces, or the resultant. That means I want to add these two arrows. So the second arrow, 16.2, is acting south. Okay? And that would be the resultant right there. This is the trajectory of the plane in the absence of wind. With the wind, it's actually going to move it off course this direction. What I'm going to do is think of these two vectors as having an angle of alpha between them. And I want to use the formula that we came up with to determine alpha, because if I take that alpha and then add it to 140 degrees, it's going to give me the true bearing of that plane. Couldn't think of what I was trying to say there. Okay, so with all that said, how do we do this? Well, the first thing I need is component forms for these vectors. Notice I've been given magnitudes and directions, but not component forms. So starting with the plane, remember this vector represents the plane, which I'm going to represent as the vector p. And this vector represents the wind, which I'm going to use the vector w for that. That would mean that the resultant is p plus w. Now, how do I get component form? Well, remember we had formulas for that. P in component form is equal to the magnitude of the vector, which is 200, times the cosine of the angle, 140 degrees, and the vertical component would be 200 times the sine of the angle, 140 degrees. Actually, scratch that. I just realized I made a critical error there. Or did I? Well, let me see. Yeah, I made a mistake there. So what I want to do is think of this as being in the plane. So if these vectors are in standard position, then I have x, y axes here that I can draw in. And if this is 140 degrees, then this angle right here is 90 minus 140, which would be negative 50 degrees. So it's actually a negative 50 degree angle. That's what I should be working with. Okay, so P, let me fix that, is equal to negative 50, or sorry, made another mistake. P is equal to 200 times cosine of negative 50. There we go. 200 sine of negative 50. Okay, that would be the component form. And we can go plug these into calculators, but I'm going to leave this as is for now. The wind, I'm going to go about this a different way. Notice the wind is pointing downwards. It has no horizontal component as I go from the initial to the terminal point, so its horizontal component would just be 0. Its vertical component would be negative 16.2. Because I'm moving downwards, that's the negative, and I can see just from the magnitude of this vector that it has a change of 16.2 going from my initial to my terminal. Okay? So now, what do we need? Well, I need to find P plus W. I need its magnitude, and I need its actual bearing, which we're going to use we're going to find alpha to determine that. So how do I find the magnitude? Well, magnitude of P plus W, I first need to know what P plus W even looks like. In component form, I'm just adding these components. That's 200 cosine of negative 50 degrees plus 0, so don't even bother writing that. And then 200 sine of negative 50 degrees plus negative 16.2, so minus 16.2. That would give me the component form of this vector. Now, if I found the magnitude of this vector, well, what that represents is that would represent the length of this arrow, which in the context of this problem is the true speed of the plane, or we can call that ground speed. Okay, if I were to compute this, remember that's the sum of the squares of these components. Now, I'm going to keep things kind of brief here. I'm going to do this just for shorthand. because all of this is going to go into a calculator anyways. And in this case, once we plug all of this into a calculator, we're going to get a speed that's approximately 212.7 miles per hour. That's what we would call the true ground speed. That kind of makes sense. If you think about it, the plane is traveling this direction, and the wind is blowing partially in this direction. Notice the wind's not blowing in an opposite direction, something that's going to slow the plane down. It actually would give the plane a little bit of a boost. It's going to speed it up a little bit. 212.7 miles per hour seems to make sense. How do I get that angle theta now? Well, the two vectors that I'm looking for angles between are p plus w and p. So using my formula, cosine of theta is equal to the dot product of p plus w with p over the magnitude of p plus w times the magnitude of p. Well, the dot product, notice I'm multiplying the components here. So I'm multiplying p to p plus w, it's x components. So that's going to give me 200 times 200, that's 200 squared. Cosine squared of negative 50 degrees. Multiplied this to this. And then 200 sine of negative 50 degrees times 200 sine of negative 50 degrees would be plus 200 squared sine squared of negative 50 degrees. Then I have to multiply negative 16, so minus 16.2 times 200 sine of negative 50 degrees. So it looks like a big mess. But again, this is all going to a calculator. You can actually simplify this a great deal by factoring the 200 squared out. Notice you have cosine squared of negative 50 plus sine squared of negative 50, which is equal to 1. That greatly simplifies this down. Down here, the product of these magnitudes, we know both of these magnitudes already. We just found the magnitude of p plus w. It was 212.7. The magnitude of p is the airspeed of the plane, which was 200. Okay, so all of this is going to get fed into a calculator, and what we want to do from here is calculate the bearing by taking an inverse cosine of this. So theta is equal to the inverse cosine of all this. And again, for the sake of time and space, I'm not going to compute all of that. I have the answer right here. It should be approximately 2.8 degrees. So now I called that theta, but actually if you look at the original diagram, it was alpha. So let me change those to alphas. That's specific to our problem here. Alpha is equal to that. So what is the bearing of the plane then? Well, the original bearing was 140 degrees. But that 140 degrees is getting an extra 2.8 degrees added to it, giving me 142.8 degrees. And that would be what we call the true bearing of that plane. So there's the bearing. And right here, we found the ground speed. Lengthy problem, right? There's a lot going on here, but it's a good one because it combined a lot of the different concepts that we've talked about with vectors. That's going to wrap it up for 10.8.